In this lecture, we'll have a look at what you can say about the zeros or about isolated singularities of an analytic function. So let me first recall that if you have a real function which may very well be infinitely differentiable, the zeros can look rather strange or complicated. So if I just take as an example this function, e to the minus 1 over x squared times sine of times 1 over x, if x is different from 0 and it's 0 when x is equal to 0. Then this function will have, if you look at the zeros on the real axis here now, there will be a sequence of zeros here which sort of accumulate at the origin and similar from this direction. So you get a sequence of zeros from here and here, and they sort of, these sequences converge to the origin. As it turns out, this cannot happen for an analytic function in the plane, because an analytic function, the zeros of an analytic function, they will always be isolated. In the following sense, that if you have a domain here now in C, and you know that the function is has a 0 here now at this point, then there will always be a circle here with positive radius where this is the only 0. So the function will be non-zero outside this point in this small circle here now. So this is one way of saying that this expresses the fact that the 0 is an isolated point. So why is this? Well, it follows immediately from the power series expansion. So if you know that f has a 0 at this point, then you have a power series expansion at this point, which looks like this. And then if this is really 0, then the first term here now in this power series will just be a 0 term. So a naught will be 0. Of course, it could be a 0 higher order, so there could be several ak's which are 0 here. But there will always be a first ak which is non-zero. Otherwise, they would all be 0 and the function would be vanish identically. So of course, the function which is identically 0 is an exception from this, but not an interesting one. So this means that you can always, by extracting a certain factor here now, say z minus z naught to the power n, you can, where n then represents the first term which is non-zero in the expansion here now. So if you sum from n to infinity here, you get this expression here now. So sorry, k minus n here now. Then you see that the first term here will be constant, which is then different from 0, and then you get higher order terms. So this is actually a convergent power series now, which converges to an analytic function, which is non-zero at the point z naught. And since it's non-zero, and since it's analytic, it's also continuous, it will also be non-zero in a neighborhood of that point, which actually proves the claim now. So then we know that the zeros of an analytic function are isolated. Of course, you should note that this only means that they're isolated, so to speak, within the domain where the function is analytic. If you take if you consider the unit disk here now, you can construct a sequence of points, something like this. And the closer you get to the boundary here, the closer the points will lie. And then you can, starting from this picture, construct an analytic function which has zeros at these points. If the points tend to these roots sort of get closer to the unit circle sufficiently fast, so that the following sum will converge, then if you consider 1 minus the absolute value of the point alpha k here now. You see, if this series converges, which then means that these points these values approaches 1 sufficiently rapidly, then you can actually write down explicitly such a function which looks as follows. You can write it as an infinite product of the following form. So it will be alpha k divided by alpha k absolute times alpha k minus z divided by 1 minus alpha k conjugate times z. This will be a function which is under this condition, it's non-zero except at these points. It has zeros exactly at these points, and it's analytic inside the unit's disk then. But of course, an immediate consequence is that it cannot be extended to a function which is analytic outside the unit disk, because that would violate this property that the zeros of analytic functions are isolated. By the way, such a product is called a Blaschke product, and the expression that you use here is very closely related to the Möbius transformations that we studied in the beginning, and which we will return to quite soon. Then, so then this formula will appear more natural, one might say. So when you have a function which has a zero, then you can always write the function as a certain power of this factor here times a function which is non-zero at the point z0. And then it's very natural to say that this number n is the order of the zero, and it very much works like for polynomials, you might say. Now we will also take a look at isolated singularities. Remember, we already studied a little bit this function. It's analytic everywhere outside the origin, but at the origin it has an isolated singularity. So isolated singularity means that there is a disk, and the function is analytic at all the points in here except at the center point, where it has a singularity. So what can you say about these kinds of singularities then? Well, first of all, remember that we have the Laurent expansion here now of a function which has just an isolated singularity. And the Laurent expansion looks like this. It's a sum from minus infinity to infinity of ak, and then you have z minus z naught to the power k. This is one way of writing the Laurent expansion. And once you have the Laurent expansion, there are you see that there are three different types of isolated singularities that can occur. The first case is that ak is equal to 0 for all k less than 1. So that the Laurent expansion looks like an ordinary power series expansion. And the second case is there are only a finite number of coefficients here with k less than 1, which are different from 0. So ak is different from 0 only for a finite number of k's with k less than 0. Of course, there can always be infinitely many positive k's where this is different from 0, but we're only interested in the negative ones now. And the third case is essentially that both these are wrong, so to speak. So this means that ak is different from 0 for infinitely many k with k less than 0. So these three types of isolated singularity, they have quite different behavior, one might say. So it's essential to be, it's important to be able to separate between these. So if you take the first case here now, then f has what you call a removable singularity. So it could be that the function is not defined at the point, but by expressing it by the Laurent series and then just summing up the Laurent series, which is in this case just an ordinary power series, you get a function which is analytic at the point itself and also coincides with f outside the point. So this just says that by redefining the function at the point or defining the function at the point, you can make it analytic at that point also. So an example of this would be sine of z divided by z, for example. This function is obviously not defined as it stands because you have a 0 in the denominator, but you can define it there, and the way is simply that you write this as, you expand the sine function here now by its power series, which is then essentially the ordinary Taylor expansion here now. And then you divide by z, and then you see that you get, here you get 1, here you get minus 1 over 3 factorial times z squared, and then you get 1 over 5 factorial times z to the 4th, and so on. And this will give you a convergent power series expansion, which is actually also gives you the definition of this at the point. So in this case, of course, the value at the point 0 will be 1. The next case here now, number 2, when there are only a finite number of negative terms here, then you see that, well, a typical example could be this function here, like this. More generally, if you have an f with this kind of singularity, you can always extract a factor like this from the function, and then you get times a function which is analytic at the point. Analytic and non-zero, if you like, at the point. And this behavior is called, that we will say that f has a pole. At the point z0. And what's characteristic for this kind of functions is that when you take the limit of the function when you approach the singularity, the function will tend to infinity. It will be unbounded and tend to infinity there. So this is the second type. And then we have the third case, like, for example, the one we had up here, e to the power 1 over z. This function, in this case, all the negative terms in the expansion are non-zero. Remember that the expansion actually looks like this. Yeah, so this is the third case here now, and this is called an essential singularity. So, in a sense, these are, at points like this, the function is really can behave very badly. So if you now have a function which you expect to be singular at a point, how do you decide what type it is? Of course, one way is to compute the Laurent expansion, but especially if there are many negative non-zero terms, that could be tedious and difficult. So it's useful to have simple criteria here. So for the first type, we can say that one way to decide if a function has a removable singularity, or in other words, one characteristic property of removable singularity is that f is bounded in a neighborhood of the singularity z0. In this case, it turns out that you can always remove the singularity in the sense that you can define the function at z0 in such a way that it becomes analytic in a neighborhood. This is just simply the way, essentially because of what we've already done. We know that the Laurent expansion contains no negative power terms, and so you just sum the rest of them to get the analytic function. The second point is characterized by the fact, as we said, that f tends to infinity near when z goes to z0. So if you find a function which has this property that it goes to infinity, then you can already say that you know that it has a pole. But the third case is, of course, the most difficult one. So how do you prove that a function has an essential singularity? Well, in some cases, you can simply prove that none of these conditions, that it's not of type 1 and type 2. So remember that type 1 also implies that the function has a limit at the point z0. Once you can define it as an analytic function at the point, of course, it's continuous, so the function will have a limit at that point. So if you have a function and you can show that it does not have a limit when you approach the singularity, and it does not even tend to infinity, then the result is that it must be an essential singularity. So an example of such a function is the following then. We consider just the function, the sine of 1 minus 1 over z. So here you see that at the point Z is equal to 0, what can you say at that point? Well, you can say that limit, or the limit, actually, let's for the moment just consider the case when you have a real variable here now. It turns out that this is enough to make to draw the conclusions here now. So if you take the limit when x tend to 0 in the real sense of sine of 1 minus 1 over x like this, then of course this that will not converge, because when x tends to 0, this will grow to infinity or minus infinity, and the function will oscillate between minus 1 and 1. So this does not exist. So the function cannot, since it's cannot be extended to be a continuous function even on the real line, it can certainly not be continuous at the point 1 in the complex plane. So we have ruled out case 1 then. But as you see, it's not even possible that this function tends to infinity, because if it would tend to infinity, it could not be bounded along the real axis. So sine of 1 minus 1 over x does not tend to infinity. In fact, when you study it along the real line, it's bounded. The absolute value of this along the real line is less than or equal to 1. So therefore, it cannot have this property, and so it cannot be a pole. So the conclusion that you can draw from this is that the only case which is left is the essential singularity. So f of z has an essential singularity at the point z equal to 0. As it turns out, the behavior of an analytic function near an essential singularity can be extremely complicated. So there is a theorem which is called Picard's theorem, which says the following then. We suppose that Z0 is an essential singularity of the function f. Then Picard's theorem says that in any neighborhood of Z0, f assumes all possible complex values. Possibly with one exception. So if you just, for example, take this function that we have met before, e to the power 1 over z, then you see that this function can never be 0 in any neighborhood of the origin. Actually, it's non-zero in the whole complex plane, because that's the property of the exponential function. But however small neighborhood of the origin you study, you will find that this equation will have, in fact, infinitely many roots within this neighborhood if w is different from 0. This is a really hard theorem, so we will not have any possibility to prove it in this course. But we can actually show something similar, slightly weaker, which still gives you a feeling for how complicated these functions are. And the proof of that is a quite simple one. This is what we can state this as follows. Simpler case. The values of f on any neighborhood of the essential singularity Z0 is dense in C. So this means that there cannot be any number which the values of f, so to speak, don't get near in Z0, near Z0. So to prove this, you just simply assume the contrary here now. So if there is a value which is sort of the values of f cannot get near, then there should be a neighborhood of Z0 and a number, say delta, delta, so that f of z minus this number then which is called c, absolute value, is larger than or equal to delta for all z in this small neighborhood U. This is just a way of formalizing the statement that the function cannot get near this value c in this neighborhood U, or in other words that the values of this is just the statement that the values of f will not be dense here now. But what would this lead to? Well, once this is true, once you assume this is true, you can consider the function 1 over f of z minus c. And if you assume that this to be true, you see that this must be bounded then, because this estimate will give you that this is less than 1 over delta then. And so this function must have a removable singularity then. We're in the first case here now. And this means that we can write 1 over f of z minus c as a function, say, h of z, which is analytic then. And this function could have a 0 of a certain order here now. So it could be that it's actually of this form, z minus z0 to the power n, say. But then this function is different from 0. And now by solving for f here now, you see that you can express f as a function which will have a pole of order at most n. So once you assume that the values are not dense, you see that you can conclude that the function cannot worst have a pole at the point.